topic of today's video will be Taylor series, and we'll see that the derivation of Taylor series requires some basic knowledge of power series, as we discussed in the last video, right? So I will start with the general power series centered at the point Z0. Suppose a power series represents a function fz in the circle of convergence mod of z minus z0 equal to capital R, right? And as we know that a power series always converge, and that circle is called the circle of convergence, right? And this is called the center of series, right? R is the radius of convergence. Fine. So we have some function fz which is equal to the power series representation of that function. So we can write it as, that is, fz is equal to the power series a n z minus z0 to the power n, and this n starts from 0 to infinity, right? You can see that this is the coefficient of z minus z0, and if I expand this, that will be an infinite series in powers of z minus z0, right? So I can write it as, or fz equal to, if I put n equal to 0, I will get a0, the first term, then a1 z minus z0, right? Then a2 z minus z0 whole square, and so on, right? So I have just substituted n equal to 0, 1, 2, 3, and so on. And what do we need? We need to find a Taylor series corresponding to this function fz, right? And the idea is to find these coefficients a0, a1, a2, a3, and so on in terms of this function, in terms of the value of the function at z0, right? So we want to focus to find these coefficients a0, a1, a2, and so on, right? Where a0, a1, a2 are to be determined, right? And if we want to determine these coefficients, to find the coefficient a0 in terms of function f, a good point is to put z equal to z0. If you put z equal to z0 on both sides, then all these terms will vanish, and eventually we will find value of a0, that will be f of z0, right? So put z equal to z0, right? And we'll have f z0 equal to a0, right? So this is the value of a0. And if we differentiate this series, let me call it equation number 1, differentiating series first with respect to z, right? So if I differentiate this series, I will get left hand side f dash z equal to, it will be a1 plus twice a2 z minus z0, and another term will be 3 times a3 z minus z0 whole square, and so on, right? Now differentiating it again, differentiate again, I will get f double dash z equal to, this will become twice of a2 or 2.1 a2, right? On differentiating it, because this will produce differentiation of z minus z0 will be 1, right? And this will give me 3 times 2 a3 z minus z0 plus dash, right? And you can differentiate it n times, obviously, and put z equal to z0 in second and third, right? In second and then third. If you put z equal to z0 in this equation number 2, you will get f dash z0 equal to a1, and all of these terms will be 0, right? So ultimately a1 is equal to f dash of z0, right? and putting z equal to z naught in this third equation, I will get f double dash z naught equal to, this term will be 2 times 1 a2, right? And from here a2 can be obtained as f double dash z over 2 dot 1, that will be 2 factorial, 2 times 1, right? And if you proceed in this way, right, finding triple dash f triple dash z, and then you put z equal to z naught, then the value of a3 will be f triple dash z naught over 3 factorial, right? So, or this can be written as f dash z naught over 1 factorial, right, in order to generalize it. Okay, so proceeding similarly, we can obtain an, we can obtain an, and that will be equal to the nth derivative, and that should be written in this way, f nth derivative, in parentheses write a small n, right, at z naught over n factorial, right? So I will substitute these values a naught, a1, a2 up to n in my equation number 1, right? Substitute a naught, a1, a2 in equation number 1, right? And that will give me fz equal to the value of a naught, that is f at z naught, right? And then a1, the value of a1 is f dash z naught divided by 1 factorial, right? And here we have z minus z naught. Then the value of a2 is f double dash z naught over 2 factorial z minus z naught whole square, right? And the nth coefficient will be nth derivative of f obtained at z naught over n factorial z minus z naught to the power n, so on, right? So this is called Taylor series, right, where we have these coefficients a naught, a1, a2 up to an, all are obtained in terms of the function, right, evaluated at the point z naught, and z naught is the center of this series, you can see from here, right? So this is called Taylor series, or you can write it as this way, or in summation form you can write it as fz equal to summation n equal to 0 to infinity, and you can see from here, pick up its nth term, write f n z naught over n factorial z minus z naught to the power n, right? So this is your Taylor series, right? Taylor series centered at z equal to z naught, okay? Or you can remember this one also, in expanded version it will be this series, right? And in particular, if I choose z naught equal to 0, right, then it will become Maclaurin series. In particular, if the center of the series is taken as 0 origin, then f z equal to summation n equal to 0 to infinity, and here we'll have nth derivative of f evaluated at 0 over n factorial z to the power n, and this is called Taylor's Maclaurin's series. Maclaurin's series, right? Okay. So you can see that the derivation of Taylor series use the power series, right? And since the idea is to differentiate this function again and again, right? And for a power series, the important point is a power series can be differentiated term by term, right? That's why we are allowed to differentiate this equation number 1, because A power series can be differentiated term by term. A power series can be integrated term by term. We can also integrate the both two sides term by term, right? Okay. So these are Taylor and Maclaurin series, right? And now we have Taylor's theorem, right? How this series is related to an analytic function, since we are focused on an analytic function inside some domain D. So how is it related to that function, right? We started with the power series in our last video, and then we proceeded to find this Taylor series and Maclaurin series. But the point is how these topics are related to an analytic function, right? So that relativity is given by the next theorem, that is Taylor's theorem, how an analytic function is related to a Taylor series, right? So the statement of Taylor's theorem, right? So we will start with an analytic function inside a domain D, right? Suppose fz be an analytic function within domain D, right? Then for any point z0 inside D, fz can be represented by the Taylor's series this way: f z equal to summation n equal to 0 to infinity, and the nth derivative of f evaluated at the center of the series divided by n factorial and z minus z0 to the power n, right? And valid for the largest circle centered at z0 and radius capital R, right? Right. So I will draw the domain first, right? That is mod of z minus z0 equal to R, right? So let me draw the domain first. This is our domain of any shape, right? Domain D, and a domain is always an open connected set, right, in which any 2 points can be joined by a sequence of straight lines, right, and all of those lines must lie inside the set, right? Then it's called domain. So this is our domain D, this one, right? And fz is a function which is analytic over this domain D, right? Then for any point z0 inside D, let me take a point here. You can take that point anywhere, right? Suppose I take that point z0, this point z0, right? So the theorem says that that fz function, which is analytic over this red colored region, can be expanded in this form, series form. And you can see that the series has a center z equal to z0, right? And this series is valid, or you can say that the series will converge for this circle. You can see that the center of the circle is at z0. So I will draw a circle which is centered at z0 and radius equal to capital R. And keep in mind the fact that R should lie within the boundary of this D, right? It means I will draw a circle as large as possible, but my target it will be that the boundary of the circle will completely lie inside this domain D, right? Like this one. if I take radius equal to this much, right, then my circle would be like this one. Right. So this is my circle. This radius is capital R, right, and this is a circle mod of z minus z naught equal to R, and you can see that this circle is completely lying inside this domain D, right. This circle cannot cross the boundary of D, right. Okay, and this z naught point is arbitrary. If you take that z naught point here near the boundary of that domain, then the circle will be small. Obviously the radius will be small. This circle will be like this one, right. Okay, right, and if I pick the point z naught at the middle, almost middle of this domain D, then the circle will be a big circle, right. So this z naught point is arbitrary, right. So the idea is that if fz is an analytic function over domain D, then fz can always be represented by a Taylor series, right, in powers of z minus z naught, where z naught is chosen as the center of that series or center of that circle, right. So the proof of this Taylor's theorem require a Cauchy integral formula and Cauchy inequality, obviously, and we are skipping the proof because our aim is to express an analytic function in terms of a series, right. So I will take numericals from here. Okay, let me rub this first. Example number 1, right. Expand fz equal to 1 by z about z equal to 2, right. Also find radius of convergence. Solution. Our first thing is that here z naught is actually equal to 2, right. This is the center of the series. You are required to obtain a series centered at z equal to 2, right, and keep in mind the statement of the theorem that fz should be analytic within that domain D. However, domain D is not given here, right, but at least this function fz should be analytic at this point. If you put z equal to 2 here, the value of the function will be 1 by 2, right. Okay, but this function has a singularity at z equal to 0. You can see that, and this is denominator is z. So if you put denominator equal to 0, you will get the singularity of this function, and obviously this function is not analytic at z equal to z naught, right. So you can say that this function is analytic at z equal to 2. That's why we will be able to expand this function in terms of Taylor series, right. So the basic condition is that the given function should be analytic at this center, right. If this function is analytic at this center, then definitely there will exist a Taylor series, right. But if this function is not analytic at this given point, then Taylor series will not exist, right. Then there is some another series called Laurent series that will be part of our next video, right. So clearly fz equal to 1 by z is analytic at the given point z equal to 2, and this is a very important condition or the important hypothesis of the existence of Taylor series, right. Okay, and we are required to expand it in powers of z minus 2, obviously, because the series is centered at 2. So every term of the series will containing z minus 2, right. Means the series will be having the ascending powers of z minus 2. The first term will be z minus 2 to the power 0, second term will be z minus 2 to the power 1, third term will be z minus 2 whole square, and so on, similar to this one, right. Okay, so our aim is to only find these values, f of z naught, f dash z naught, f double dash z naught, and so on, right, because you have this formula for Taylor series, right. You have this z naught is known to you, that is true. So ultimately our work is to find these derivatives of f, right, and then evaluate those derivatives at this point z equal to 2. So I will start with this fz and differentiate it. I will get f dash z, that will be equal to minus 1 over z square, right, and then I will have f of double dash z, that will be plus 2 over z cube, then f of triple dash z, that will be minus 6 over z to the power 4, and so on, right? And you can also write the nth derivative if you want to generalize it. You can see that the first derivative is having negative sign, second positive, third negative, right? So I will write the nth derivative. However, it is not usually required. You can write it minus 1 to the power, I think, n, right? Negative for first derivative, second derivative positive, odd derivative negative, even derivative positive. So minus 1 to the power n. And it is 1 factorial, 2 factorial, 3 factorial. So it will be n factorial, I think, n factorial, and z to the power n plus 1, right? Third derivative, we have z to the power 4. So this is the nth derivative, right? And it is obtained on generalizing these derivatives, right? So by Taylor series, using Taylor's series centered at this point, z equal to 2. So I will plug this z not equal to 2 in my original formula. I will get fz equal to f2 plus f dash 2 over 1 factorial, and then here we'll have z minus 2, then f double dash 2 over 2 factorial, and z minus 2 whole square, right? This is enough, but you can also write the nth derivative term, right? Nth derivative obtained at 2 and n factorial, and here we'll have z minus 2 whole to the power n, and so on, right? So I will plug these values, f dash or fz equal to, you can evaluate f2 from here, you just plug 2 here, that will be 1 by 2, right? 1 over 2 plus f dash 2. This is f dash. If you put 2 here, you will get minus 1 by 4, right? So minus 1 by 4 is z minus 2. And for f double dash 2, you should plug 2 here. That will be 2 by 8, and that will be 1 by 4. 1 by 4, and here we will have 2 factorial. That will become 1 by 8, right? Z minus 2 square, and so on. And the nth derivative, that is minus 1 to the power n, and this n factorial will cancel with this one, over 2 to the power n plus 1, right? And z minus 2 whole to the power n plus dash dash, right? So this is the Taylor's expansion of this function about the point z equal to 2, right? And again, you can see that since this function was analytic at z equal to 2, so you can see that this is a Taylor series, and all the powers of z minus 2 are positive powers, and it indicates that there is no singularity at z equal to 2, because all the powers of z minus 2 are positive powers. Had there been negative powers of z minus 2, then z minus 2 will appear in the denominator, and on putting z equal to 2 will get singularity at z equal to 2, because the denominator will become 0 in that case, right? Okay, now another point is to find the radius of convergence, right? And since you can see that this series is centered at z equal to 2, right? And you need to find the radius of convergence, and imagine that circle of convergence, right? Circle of convergence, right, is the largest circle that is centered at the given point. Our point is z equal to 2, and that circle must be drawn inside the domain D, right? And within that domain D, the function should be analytic, and we know that this function, our function, is not analytic at z equal to 0. So you are standing at z equal to 2, right, on the z plane, and you know that z equal to 0 is a singularity, right? So the circle will be, the largest circle will be that centered at z equal to 2 will be of radius 2, right? Because your circle cannot cross z equal to 0. If you are standing at z equal to 2 and you want to draw a circle centered at z equal to 2, then your radius should be equal to 2, not more than 2, because if you take your radius more than 2, then your circle will enclose at z equal to 0, right? And in that case, your function will not be analytic inside the circle of convergence. And there is a important hypothesis of this Taylor's series, that your function should be analytic within your circle of convergence, right? Therefore, be careful to not enclose your singularity, right? Your center is z equal to 2, right? And your singularity is z equal to 0. So the radius is the distance between z equal to 0 and z equal to 2, and that is 2, right? So I will write a point here, that radius of convergence convergence is actually equal to the distance between the center and the nearest singularity. If there are so many singularities, then the distance between the center and the nearest singularity will give the radius. This time we have only one singularity, that is z equal to 0. So the distance between the center and singularity will be the radius of convergence, right? Distance between center z equal to 2 and nearest singularity, right? And obviously that nearest singularity is z equal to 0, so our answer will be 2 because the singularity is at z equal to 0, right? Okay, taking another example. Example number 2, expand fz equal to z plus 1 over z minus 3 z minus 4 about point z equal to 2, right? Also find radius of convergence, right? This time I have taken a complicated function as compared to my last example, right? Solution. And the first important thing is to check the behavior of the function at this point, right? If you plug z equal to 2 here, right, then you will get some value. Obviously z equal to 2 is not the singularity of this function. However, 3 and 4 are the singular points of this singularities of this function, right? So we can say that this fz is analytic at this point, right? Clearly fz is analytic at the given point z equal to 2, right? And this is the center of our series. So obviously we can proceed in that way also, of finding f dash, f double dash and f triple dash and so on. You can derivate this function using quotient rule of differentiation, right? But this time we'll use another method, right? Alternate method, I should say, using alternate method, or that is also called geometric progression method, right? Using method of geometric series. I will convert this function in terms of two geometric series and then we'll get the answer. Geometric series. However, you can use that method for this case also, that is fine, right? So the another method, in order to use this geometric series method, you first express your function in terms of partial fractions, right? So using partial fraction, fz equal to, can I write it directly? Z plus 1 over z minus 3 z minus 4, right? And I need z plus 1, okay. 16, 9, 16 and 15, I think, yeah. I think it will give 16, 5 and 1 over z minus 3, and this is z minus 4, right? Put minus sign, and yeah, I should write 4 here, 4 and 3 here, right? And if I take 15 and 16, if I take 5 here and 4 here, I think 5z minus 4z will be z, and minus 15 and plus 16, that will be 1, right? Fine. Okay, using partial fractions. Using partial fractions, right? Or you can use this hit and trial way to write these fractions directly, right? Okay, fine. Then these two different functions, I will apply geometric series for both of these functions, but remember that the center of the series is 2, means that the answer will be containing powers of z minus 2, right? And in order to get a series, geometric series in powers of z minus 2, I have to write this denominator in terms of z minus 2 and this also, right? So I will write it as 5 times and yeah, over 1 over z minus 2 minus 2, right? And this, for this I will write 1 over z minus 2 minus 1, right? Because we need a series that should contain ascending powers of z minus 2, so I have to produce z minus 2 at this step anyhow, right? So notice this step. Okay, then taking this minus 2 common, because I need z minus 2 here, and I will take negative common out of it, so it will become minus 5 by 2, taking 2 common from the denominator, and here I will have 1 over 1 minus z minus 2 over 2, right? And taking negative sign common, I will have 1 over 1 minus z minus 2, right? Now we can apply the geometric series. We can take this on the numerator, that will give minus 5 by 2 and 1 minus z minus 2 over 2 whole to the power minus 1 and plus 1 minus z minus 2 whole to the power minus 1. Then we'll apply geometric series here. 1 minus alpha to the power minus 1, that is 1 plus alpha square and so on, and same for this one, right? So applying geometric series for both of these two terms, minus 5 by 2 equal to 1 plus this alpha z minus 2 over 2 and then alpha square z minus 2 over 2 whole square, right, and so on, infinite series. Similarly for this one, 4 1 plus z minus 2 plus z minus 2 whole square and so on, right? And then you can pick the like terms like this minus 5 by 2 and plus 4, and it can be written as 3 by 2, right? This one and this one, and then this will become minus 5 by 4 and this will be 4. So minus 5 by 4 plus 4, that will be 16 minus 5, 11 by 4 plus 11 by 4, right? Okay. And then the third term, right? This is by 4 and 4 to 8, right? Minus 5 by 8 and this will give you plus 4, right? So 32 minus 5, that will be 27. So 27 by z minus 2 and 27 by 8 and z minus 2 whole square and so on. So this is your answer, right? So you can see that you obtained fz in powers, ascending powers of z minus 2, right? 2 is the center of this series. So first part is completed. Now focus on the second part, find the radius of convergence. And as we did in this first example, the radius of convergence is the distance between the center and the nearest singularity, right? Now you can see that we have two singularities at z equal to 3 and z equal to 4, right? I will write it here. Note z equal to 3 and z equal to 4 are singularities of fz, right? And the center is 2, right? So the radius of convergence will be the distance between the center and the nearest singularities, and the nearest one is z equal to 3. Z equal to 3 is the nearest to z equal to 2, right? So the radius will be equal to 1. I will write that here. Yeah. Therefore, radius of convergence is equal to the distance between the center, that is z equal to 2, and the nearest singularity, that is z equal to 3, and we'll subtract those numbers. Distance between any two complex numbers, z1 and z2, can be obtained by writing mod of z1 is the center, 2 minus z2, and z2 is the nearest singularity. I am taking as 3, and the answer will be plus 1, right? Because that is radius is always positive. Now taking another example. Example number 3, expand fz equal to 1 over z square plus 4 about z equal to iota, right? Or should we take z equal to 1, right? Okay. Also find radius of convergence. Also find radius of convergence. The solution. The first thing is to notice that this function is analytic at this point, z equal to 1, right? Clearly, fz is analytic at z equal to 1, and we'll find the singularities of this function. You should put the denominator equal to 0, and that will give you z equal to plus minus 2 iota, right? The singularities are at z equal to iota and minus iota, sorry, 2 iota and minus 2 iota, 2 iota and minus of 2 iota, right? So these are the singularities of this function. Okay, now again, using this method of geometric series, I should factorize it z minus 2 iota and z plus 2 iota, and then you can use your partial fraction technique, minus 1 over z plus 2 iota, and that is producing 4 iota here. So I will balance with 1 over 4 iota. Okay, so using partial fraction you can write this. And now, since I need the series about 1, so the powers will be z minus 1 in my series, right? Or should I choose it z equal to iota, right? Okay, z equal to iota, fine. Then it will become 1 over 4 iota, and yeah, it will become 1 over z minus iota, right? And you will write it as z minus iota plus 3 iota, because you need z minus iota, right? And if I take minus iota common from here, right, then it will produce plus 1 by 4, yes. And inside bracket I will be having 1 minus z minus iota over, since minus iota was taken common, right? Okay, then okay, fine, minus iota, right? And from here you should take common 3 iota, right? So 3 iota, you take 3 iota common, then 3 into 4 will be 12, minus 1 by 12, minus 1 by 12, and here you will have 1 over 1 plus z minus iota over 3 iota, right? Now you can use the geometric progression for each of these two terms. This will give you 1 by 4, and taking it on the numerator part and then expanding it, I am not writing that step again and again. So that will give you 1 plus z minus iota over iota, and then z minus iota over iota whole square, and so on, right? Minus 1 by 12, 1, and when you take this 1 plus this or minus 1, then there will be alternate terms, negative and positive. First will be 1, then negative sign z minus iota over 3 iota, and then positive sign, right, z minus iota over 3 iota whole square, and then negative, and so on, right? And now you can add the like terms, like this is 1 by 4 and this is minus 1 by 12, right? So you can add them, and that will give you it is actually 3 by 12 and minus 1 by 12, so it will be 2 by 12, so 1 by 6, 1 by 6, and this is your 1 over 4 iota, and this is a minus 1 upon 36 iota. So 1 over 4 iota minus 1 upon, no, it will be plus, I think, plus 1 upon 36 iota, right? So you can write it as 9 upon 36 iota, so 10 upon 36, right? And that will produce 5, 18, right? 5 by 18 iota plus 5 by 18 iota and z minus iota, right? And similarly for the z minus iota square term, right, that will give you 1 minus 1 by 4, and this will give you negative, right, and then iota square positive, right, plus 9 into 12, 108, right? And on taking LCM it will give you plus 1, minus 26 upon 108, right? And you can cancel that term, 13 by 54 minus 13 by 54 z minus iota whole square, and so on, right? So this is your expansion in powers of z minus iota, right? The center of the series is iota, and the singularities are at 2 iota and minus 2 iota, right? So if you compare the distance of your center from these two singularities, the nearest one will be 2 iota, because you are standing at iota, right? So 2 iota will be at a unit distance from iota, right? While minus 2 iota will be at a distance of 3 units from it, right? Therefore, radius of convergence is the distance between the center, and the center is iota, minus, sorry, z1 minus z2 is the formula for distance. So z1 is the center and z2 is the nearest singularity. So you should pick the nearest singularity, that is 2 iota. You should plot those points iota, 2 iota and minus 2 iota on graph, and you will see that 2 iota is the nearest one, right? And this time the radius will be equal to 1, because this will be minus iota and modulus of minus iota is equal to plus 1, right? Taking last example. Example number 4. Expand fz equal to sin z over z minus pi about z equal to pi, right? Solution. First thing is to notice is that this point, at this point, this should be analytic, right? And if you put this z equal to here, then you will get sin pi, z equal to pi here, sin pi over pi minus pi, it is 0 by 0 form, right? So you're getting 0 by 0 form. It indicates that it is not a singularity, obviously. 0 by 0 form is indeterminate form, and applying LH rule, you can obtain the value of the function at z equal to pi. I think you should differentiate the numerator and denominator in order to use that LH rule, right? That will be cos z over 1, and cos z evaluated at pi will give you minus 1. It means that at this point the function is analytic, right? So you can always use the Taylor series, right? So writing your fz in this fashion, sin z over z minus pi, right? You need to expand it in terms of z minus pi. First thing is that, means if you expand this, every term should be of z minus pi term, means z minus pi to the power 0, z minus pi to the power 1, and so on, right? So be careful at this point. Do not expand this, right? While you know the expansion of sin z, and if you expand this sin z, your expansion will contain positive powers of z, but we need positive powers of z minus pi, right? So you should do some manipulation on this z in order to obtain this z minus pi, as you did here at this point, right? So wherever you have this z, just try to write it in this form, sine of z minus pi and plus pi. It can always be written in this way, right? And in the denominator you are always having z minus pi, right? Now you should apply sine pi plus theta. This is a theta, sine 180 plus theta, and that is equal to minus of sine theta. So minus of sine z minus pi over z minus pi. Now at this point you are in position to apply the expansion of sin z minus pi, right? Because you need that expansion in powers of z minus pi. So now expand this sine function. Negative sign is taken out, z minus pi is also taken out. Expansion of sine, treat it as theta, sine theta, that will give you theta minus theta cube over 3 factorial, and then plus theta to the power 5 over 5 factorial, right? This is an expansion of sine theta, right? Very familiar expansion. And then you take this z minus pi inside, you will get minus 1 as the first term, then plus z minus pi whole square over 3 factorial, right? And then minus z minus pi whole to the power 4 over 5 factorial, and so on. So this is the required expansion, right? And what will be the answer if I ask the radius of convergence, right? You can see that this function has no singularity at all. You cannot say that this function has singularity at z equal to pi, because when you are plugging z equal to pi in this function, you are getting 0 by 0 form, and on applying LH rule you are getting minus 1, right? Okay, so there is no singularity at all for this function, right? And the radius of convergence is the distance between the center of the circle and the nearest singularity, which you don't have in this case. Your series is centered at z equal to pi, but there is no singularity. It means that the radius will be infinite, right? So actually this function is an analytic function. That's why radius of convergence will be infinite. So if you want to write the circle of convergence, that will be mod of z minus pi less than infinity, right? Okay, so taking one more example, right? A short one, example number 5. Example number 5, and if fz equal to 1 over z square plus 1, right, has Taylor's series representation of the form summation k equal to 0 to infinity a k, I should write it as ck, changing the coefficient, ck z minus a whole to the power k, right? Then find the radius of convergence. Then obtain the radius of convergence, right? You can see that this is the function fz, and its Taylor series representation is given you, right? You need not to find the expansion of this fz because it is given to you, right? And this time the coefficient is ck, and this is the series is centered at z equal to a, right? And what is this a? A can be any real number. I should write here a is a real number, right? A belong to real number, right? Okay, and you have to obtain the radius of convergence, right? And using that fact that radius of convergence is the distance between the center and the nearest singularity, right? And what are the singularities of this function? And singularities are obtained by putting denominator equal to 0 generally, right? So z square plus 1 equal to 0, right? When you put denominator equal to 0, just keep in mind one fact that the numerator should not be equal to 0 at that point, like in this example, right? If we say that roughly, we say that put denominator equal to 0 in order to find singularity. So if someone put z minus pi equal to 0, he will get z equal to pi as a singularity. But there is a danger, because putting z equal to pi in the numerator, that is producing 0 in the numerator also. So be careful at this point when you try to find the singularity of a function by putting denominator equal to 0. Just be careful that at that point the numerator should not vanish, right? Okay, so here we can say that because the numerator is 1, there is no non-zero, right? So you can put denominator equal to 0 in order to find the singularity, and obviously those singularities are plus minus eta, right? And at those singularities the numerator is non-vanishing, right? Okay, so be careful at this point. Solution: clearly z equal to plus minus eta are the singularities of fz, right? And the center of the series is z equal to a, right? Z equal to a is center of series or center of circle, whatever, right? Circle of convergence, right? Okay, so radius is equal to distance between center, and the center is z equal to a, and the nearest singularity. And what is the nearest singularity, right? Center is z equal to a, and the singularities are plus minus eta, right? So in this case you cannot decide which is nearest to this a, because this a is unknown. A is just a real number. This a can be anything, right? But which one is the closest singularity to a? You should draw the graph here. If I draw the graph, z equal to a is a real number, so that will obviously lie on this x-axis anywhere, right? Because this is a real number. You cannot plot a here, here, or on y-axis. That point should be here, z equal to a, right? This point is a, right? And plot your singularities. Those are plus minus iota. So this is a singularity plus iota, and this is another singularity minus iota, right? So no matter what is the value of a, right, unless and until it is on x-axis, both of these singularities are at equal distance from this a. You can see that this is an isosceles triangle, right? This x-axis is just the center of these iota and minus iota, right? This is the bisector, right bisector of these line joining these 2 points, right? So you take a anywhere on this x-axis, both of these similarities are at equal distance, right? So you can always find the minimum distance. Either you choose the distance between a and iota, or you choose the distance between a minus iota. The answer will be same, right? Because a is at the bisector of these, the line joining iota and minus iota, right? So distance will be given by taking the distance between center and any of these singularity. I have taken iota, right? And since it is a real number, right, it is a complex iota and its imaginary part is 1, so the answer will be under root of a square plus 1, right? And the important point is that this a will lie on the right bisector of the line joining iota and minus iota, right? This is the radius of convergence. So this is it for Taylor series, and remember that the Taylor series can only be obtained if and only if the function fz is analytic at that point. Means the point you are taking the center of the series at that point, the function should be analytic at that point, right? And what happens if the function is not analytic at this point, right? So that will be the part of our next video, and that series has a special name that's called Laurent series. We'll do that in our next video. For this video, thanks.